Chapter 19: Additive Processes, Rapid Prototyping, and Direct Digital Manufacturing. Introduction. Casting processes, processes that produce shaped containers. Deformation processes, it exploits the plasticity of certain materials and use mechanical forces to rearrange solids into a more desirable shape. Material removal process, begin with an oversized solid and progressively remove unwanted segments to create the desired products. Consolidation process, process in joining discrete pieces of material. Additive processes, new grouping of processes that create a desired shape by the incremental addition of material in a layer-by-layer fashion. Prototypes. Prototypes provides a physical representation of the product that can be used to assess a designer's success in achieving a part's form, fit, and function. First topic is the area of applications. It can be divided into 4 groups. The first group is the rapid prototyping. Next property is the production of scale models to enhance visualization or for purposes such as wind tunnel testing. Next, rapid tooling. The production of tooling to use in another process such as foundry patterns, cores or molds, or jigs and fixtures for machining or joining processes. And lastly, direct digital manufacturing. The manufacture of finished products directly from a computer file with no intervening tooling. Rapid prototyping and direct digital manufacturing. They are additive processes, building the shape progressively through the accumulation of thin layers. They are free-form fabrication processes capable of producing any required geometry, providing that the dimensions fit within the working envelope of the experiment. They are also tool-less manufacturing processes, able to make any product geometry without requiring part-specific tooling. So these are the graphs and tables of rapid prototyping and direct digital manufacturing. The parts are UV laser beam, platform, vet, UV curable liquid polymer, layered prototype, and elevator. Additive processes, pre-processing. It is the conversion of three-dimensional computer-aided design into the set of instructions that will be used to control and direct the manufacturing tool. Bases and supports can be added to the part during the stage. Post-processing include operations as the removal of bases and supports, removal of excess uncured resin, firing, or sintering to increase strength, mechanical fishing to remove stair-stepping artifacts or additional curing operations. Layer-wise manufacturing. They are additive processes that can be classified by the nature of material disposition. There are 3: liquid-based processes, powder-based processes, and deposition-based processes or solid-based. Computer-aided design to computer-aided manufacturing. The process begins by converting the geometry of the part into stereolithography or STL files, beginning with a process known as tessellation. Reverse engineering. It replicates an existing product. Rastering, wherein a two-dimensional area is reduced to a series of specified width and space lines. In summary, the CAD to CAM conversion begins with a three-dimensional solid that is then sliced into a series of two-dimensional layers, each of which is further reduced into a series of linear tool parts. Thickness control, stair-stepping, and surface finish. Stair-stepping is all forces not perpendicular to the slice plane, example, curved faces, rounded corners, and tapered sides, are approximated by the edge of stack, uniform thickness layers. In general, the surface finish of the liquid-based processes is better than that of the powder-based approaches. Voxel geometry. Voxel geometry is a useful concept in understanding the scanning types of layer-wise disposition. Determines the thickness of the layers, the distance between adjacent scans, and ultimately, the number of layers and scans needed to complete a part, as well as the resultant surface finish. Voxel is the volume element and is the three-dimensional equivalent of the pixel in a two-dimensional image. Also describes the depth, width, and breadth of the material that is effectively being altered by the energy or deposition of being scanned. This is the graph of stair-stepping. Dimensional precision. It is a specific operating conditions its specific operating conditions can greatly affect dimensional accuracy. A product fabricated under one set of processing conditions may have a different overall accuracy than one built under a different set of conditions. Hatching is filling in the cross-sectional area and could occur in a straightforward manner if the material did not experience the shrinkage. On a more macroscopic scale, the interior temperatures of a solid part tend to exceed the surface temperature during the build process. Supports. Supports is the extra material used to support segments of the material layers that do not have solid material underneath. May be required when the geometry contains segments that are cantilevered out from the main body. Build time. Build time consists of three major components: pre-processing, fabrication, and post-processing. Pre-processing involves the creation of CAM software necessary to drive the machinery, and the required time has been reduced considerably by advances in the capacity and speed of computers. Fabrication is the largest component of both time and cost, with variation depending on the specific process, part size, part complexity, and batch size. Post-processing involves cleaning and finishing the product after fabrication. Liquid-based processes. Liquid-based processes can be classified into three: stereolithography apparatus, solid ground curing, and inkjet deposition or droplet deposition manufacturing. Stereolithography apparatus. This was made possible by a series of technological advances including high-speed computers, computer-aided designs, precise motion control, UV lasers, and photocurable polymers. The advantages of SLA is its high dimensional accuracy and good surface finish. The disadvantages of SLA is the use of expensive photopolymer resins. Material costs are approximately $0.30 or 30 cents per cubic centimeter or $5 per cubic inches. Generally, not performed in an office environment. This process may not be attractive for parts with multiple free-hanging segments because each will require support. Additional scanned layer polymerization processes have been developed by modifying certain features of the SLA technique. Mask clamp descending platform is an approach where photomasks are created for each layer and are positioned above the resin surface. A single photo exposure forms the entire layer as opposed to the serial laser scan, thereby decreasing the required build time. Ascending surface. Ascending surface is an approach where the base and partially built solid remain fixed and a pre-measured amount of uncured resin is added to the chamber to create each new layer. This is an example of a product made from stereolithography apparatus. Solid ground curing. Cures layer upon layer of photopolymer with a photomask and high-intensity UV lamp similar to the mask lamp descending platform method, but the details are somewhat different. Dimensional accuracy with the SGC process tends to be good. Claimed accuracy for the process is 0.1% up to the maximum of 0.5 meter or 0.02 inches. Advantages of solid ground curing is the time to build every layer is the same, independent of either part geometry or the number of parts being built. The disadvantages of solid ground curing is its complexity, large number of process steps leading to larger, heavier, and more expensive equipment. This graph shows the process of solid ground curing. Inkjet disposition or droplet disposition manufacturing. It creates the individual layers by selectively depositing molten materials, wax, thermoplastic polymers, or low melting point metals onto a substrate as a series of uniformly spaced, uniform-sized microdroplets, often at rates of several thousand per second. Dimensional accuracy is good. Build times tend to be long. To improve build time, multiple jets may be incorporated into a single printhead, and alternative hatching patterns may be used when solid products are not required. This graph shows the representation of the process of inkjet disposition. It starts with the inkjet printing head, and it shows droplets of molten material within the elevator. Powder-based processes. Powder-based processes includes four processes: selective laser sintering, selective laser melting, electron beam melting, three-dimensional printing, and sinter mask. Selective laser sintering and selective laser melting. Like most of other processes, these also begin with the same part CAD file that is sliced in the STL format and a vertically positioned elevator. Because of the excess powder acts as natural support, the SLS process will not require the design, fabrication, and removal of support structures. SLA uses one of the broadest range of build materials, including plastics, waxes, such as those used in investment casting, metals, ceramics, and particulate composites. Fusion, primary mechanisms for binding particles. Semi-crystalline materials such as nylon are locally melted and can essentially produce fully dense parts. Radiant heaters. It is used to bring the powder to temperatures just below the fusing point. Dimensional accuracy and surface roughness tends to be poorer than other additive processes. This is the graph showing the process of selective laser sintering and selective laser melting. The diagram shows CNC machining flowgram, which starts from obtaining preform. Next is design fixtures. Next is select consumable tooling. Next is create toolpaths. Next is verify toolpaths, build fixtures, machine part, and lastly, inspect the part. The total process time is 14 days minimum. Next diagram is the direct manufacturing, where it starts in creating STL file, setup build, verify build, prep machine, run build, breakout build, post-process, and inspect part. Total process time is 4 days. Electron beam melting. Another powder-based scanning beam process where the higher power of electron beam can be used to produce full-density metal products from layers of metal powder. Used to produce fully functional products, especially in areas where strength and elevated temperature performance are required. Applications include injection molding dies, die casting tooling, stamping tools, as well as finished product for the direct service, such as aerospace parts and orthopedics implants. This is the graph showing the process of electron beam melting. Three-dimensional printing, also known as selective inkjet binding, begins by loosely depositing a thin layer of powder for processing. Primary assets of 3D printing. Variety of engineering materials that can be used. Virtually any material that can be obtained as powder including metals, ceramics, cermets, and polymers. Elimination of thermal residual stresses and their related problems because of the absence of thermal processing during the build. Also offers some of the fastest build times of the additive processes. This is the graph showing the process of three-dimensional printing. Sinter mask. Relatively new additive manufacturing process that melts layer of thermoplastic powders using masks. The average layer time for a sinter mask machine is approximately 4 seconds, which compares to an average layer time of 30 seconds on selective laser sintering process using the same material. Comparing the two processes, sinter masks offer a 15-hour time saving. Deposition-based processes. Deposition-based processes can be classified into 4. Fuse deposition modeling, laser-engineered shaping and direct metal deposition, laminated object manufacturing, and other deposition-based processes. Fuse deposition modeling. It produces laminated three-dimensional objects through a robotically guided extrusion of a commercial-grade thermoplastic material. The build cycle in this process is much simpler than other additive manufacturing processes. Disadvantages. It has a limited selection of engineering materials which includes machinable wax, investment casting wax, polycarbonate, polyphenol sulfone, and acrylonitrile butadiene styrene or ABS. Common defects of the process is it has gaps between contour perimeter traces and the restored field traces. It also has voids between restored field traces when the extrusion carriage makes a 180-degree direction reversal. Visible hatch lines due to the extrusion of round profile material is also visible. This is the graph of the process of fuse deposition modeling. It has a thermoplastic filament and the FDM head melts plastic through the filament supply. Laser engineered net shaping LENS and direct metal deposition DMD. In DMD, Lasers and powders have been combined to enable the direct fusing of uncoated metal powders into fully dense functional metal products. In lens, the high-power laser produces a tiny molten pool on the surface of a build, and a nozzle blows a small amount of metal powder into the pool to increase its volume. These processes are microscopic and computer-controlled version of laser candling, performed in a controlled atmosphere chamber, typically argon, to prevent undesirable oxidation. Major drawback. The major drawback is its long layer times that can lead to build times in weeks or months for large parts. Laminated object manufacturing involves the sequential bonding and patterning of solid material sheets or laminate, with a common process variation using sheets of papers with a thermally activated organic compound coating one side. Its unique characteristics is its method for extracting the product after the fabrication. Equipment and materials tend to be cheaper due to the simplicity of the process and reduced maintenance requirements. With paper laminates, the properties of the finished product are similar to those of bitumen. This is the graph showing the process of laminated object manufacturing. Its parts consist of mirror, moving optics head, tile, layer contour, block, take-up roll, platform, supply roll, sheet material, heated roller, and laser. Other deposition-based processes. First process is the ultrasonic consolidation. It is used to bond layers of metal foil onto full density products. The next one is the polyjet conceptual model. Uses inkjet approach to deposit droplets of liquid photopolymer, which are immediately cured by exposure to ultraviolet light, while a second system deposits a non-curable support material. The uses and application. In less than 3 decades, additive manufacturing processes have evolved from a method of making low-strength 3-dimensional plastic design prototypes to a family of processes that are changing the way organizations design and manufacture products. Prototype manufacture. It is a large number of additive products are used to produce both conceptual models and functional models to assess aspects of form, fit, and function. In converting a design concept to a physical representation offers the following advantage. Rapid tooling. It is an excellent application for additive manufacturing processes. The simplest of the rapid tooling approaches is the direct production of patterns or molds used for metal casting. First is investment casting. It is frequently used to manufacture intricate parts that are difficult to machine, forge, or cast by other methods. Die casting dies can be produced with internal cooling channels that are positioned for optimum performance. Molds have been produced to perform the blow molding of prototype polyethylene and PET containers. There are also a number of manufacturing tools that are used within the manufacturing system, including jigs, fixtures, templates, and codes. Direct digital manufacture. It is producing finished products direct from digital data, eliminating all tooling. Pros, cons, and current and future trends. Additive manufacturing has grown from a concept to a diverse and fully developed manufacturing family in less than 3 decades. The properties are expanded from low-strength photopolymers to now include engineering plastic and elastomers, ceramics, metals, and even composites. It has good tensile and flexural strength, good impact resistance, reduced anisotropy, and metals have moved to full density with properties equivalent to wrought and cast products and now range from low-strength, low melting temperature metals through titanium, tool steels, and superalloys. Range of availability and cost. Available materials are still limited. Raw material costs are often high.
Chapter 20 Fundamentals of Machining and Orthogonal Machining. Machining is the process of removing unwanted material from a workpiece in the form of chips. If the workpiece is metal, the process is called metal cutting or metal removal. Statistics have shown that in the US industries, they spent $100 billion to perform metal removal operations. The process of metal cutting is complex because it has such a wide variety of inputs. The metal tool selected to perform the process, the cutting tool selected, and the process and parameters of the workpiece. Here are samples of the inputs: machine tool selections, lathe, milling machine, drill press, grinder, saw, broach, or machining centers. Another input is cutting tool parameters: tool design geometry, tool angles, nose radius, edge radius, material, hardness, finishing, and coating. Some workpiece parameters are predeformation, metal type, BCC, FCC, HCP, SFE, or purity. Cutting parameters are such as depth of cut, speed, feed, environment, oxygen, lubricant, and temperature. And of course, work holders. Machining processes are maybe oblique that has a single point cutting and multiple edge tool. It is turning single point tool process, or maybe orthogonal. It is a macro industrial studies performed on plates and tubes, macro studies carried out in microscopes using high-speed photography. Outputs may be measurements and determinations. Here are 7 basic chip formation processes: turning, drilling, milling, grinding, sawing, planing, shaping, and broaching. Speed is a primary cutting motion which relates the velocity of the cutting tool relative to the workpiece. It is generally given in the units of surface feet per minute as FPM, inches per minute IN/IMIN, meters per minute, or meters per second. The selection of the cutting speed determines the surface speed of the rotating part that is related to the outer diameter of the workpiece. It is given with the equation V is equals to pi diameter 1 times NS over 12, where D1 is the inches, V is the speed in the surface feet per minute, and NS is the revolution per minute of the workpiece. The operator inputs the desired revolution per minute in the spindle into the lathe to produce the desired cutting velocity. Feed. Feed is the amount of material removed per revolution or per pass of the tool over the workpiece. In turning, feed is inches per revolution, and the tool feeds parallel to the rotational axis of the workpiece. Depending on the process, feed units are inches per revolution, inches per cycle, or inches per tooth. Depth of cut represents the third dimension. In turning, it is the distance the tool is plunged into the surface. It is the difference in the initial diameter D1 and the final diameter D2. It is given by the equation depth of the cut is equals D1 times D2 over 2 is equals to D. Here is the diagram of the turning and lathe tool. The RPM of the rotating workpiece is NS. It is established the cutting speed V at the tool according to NS. NS is equal to 12 times V over pi times D. The depth of the cut is D is equal to D1 minus D2 over 2. The length of the cut is the distance the tool travels parallel to the axis of L. Workpieces are held in work holding devices. In the shown figure, a 3-jaw chuck is used to hold the workpiece and being rotated against the tool. The chuck is attached to the spindle, which is driven through the gears by the motor. In Metcut's data handbook, he gives a recommendation of the starting value of cutting speed and feed for a given depth of cut, a given work material, a given process, which is turning. Cutting speeds can be increased with the carbide and coated carbide tool materials. Thus, we see that to process different materials, the output parameter to the machine tools may be determined. For lathe, the input parameters are DOC or depth of the cut, the feed rate, and the RPM value of the spindle. The RPM value depends on the selection of the cutting speed. Rewriting the equation for NS would be NS is equal to 12V over pi D1, congruent to 3.8V over D1. Other machining process done on lathe machine is boring. It is enlarging hole of diameter D1 to diameter D2. Boring can be done with multiple cutting tools, feed in inches per revolution as well. Facing, tool feeds to center of workpiece, so L is equals to D over 2. The cutting speed is decreased as the tool approaches the center of the workpiece. Grooving, parting, or cut off. Tool feed perpendicular to the axis of rotation. The width of the tool produces the depth of the cut. Basic milling process. First basic milling process is slab machine. Slab milling. Slab milling is usually performed on a horizontal milling machine. Equations for Tm and MM are derived. The tool rotates at revolutions per minute in NS or feed. The workpiece translates passes the cutter at feed rate FM. The feed. The length of the cut, L, is the length of the workpiece plus allowance, LA. LA is given by the equation LA is equal to square root of D squared over 4 minus D over 2 minus D squared. Tm is given by the equation L plus LA over Fm. Next basic milling process is face milling. Given a selected cutting speed V and a feed per tooth, the RPM of the cutter is NS is equals to 12V divided by pi D for a cutting of diameter D. The feed rate is Fm is equals to F1N times NS for a cutter with teeth. Basics of broaching. Basics of broaching. The diagram is shown in the PowerPoint. Tm for broaching is equals to L over 12 times V. The MRR per tooth is equal to 12T times WV, where V is the cutting velocity in FPM, W is the width of cut, and T is rise per tooth. Basics of shape process. The tool cuts at velocity V with the return velocity of VR dictated by the RPM of the crank and S. The cutting speed V is equals to 1 plus A and S over 12 RS, where RS is equals to stroke ratio is equals to 200 degree divided by 360 degree, and the length of the stroke is 1 equals L plus allowance. The tool feed is FC per stroke. Tm is W1 and SFC. MRR is equals to LD and SFC in inches cubed per minute. Now you can see here is the relationship of the crank RPM NS to the cutting velocity V. Here are the operations and machines used for machining cylindrical surface. Turning, we have lathe and C lathe. Machining, center. Grinding, we have cylindrical grinder. For sewing, we have consor or band saw. For drilling, we have drill press, machining center, vertical milling machine. For boring, we have lathe, boring mill, horizontal boring machine, and machining center. For reaming, we have lathe, drill press, boring mill, horizontal boring machine, and machining center. For grinding, we have cylindrical grinder, and sewing, we have contour of bandsaw. For broaching, we have broaching machine. Now for the operations and machines used to generate the flat surface is also presented in the table. Here are the summary for shop equations. Shop equations are the shop formulas for cutting speed, revolution per minute, feed rate, feed per revolution, cutting time, rate of metal removal, horsepower required at spindle, horsepower required at motor, torque at spindle, and symbols. Some basic machining process. We have turning, engine lathe, turning CNC, turning automatic screw machine, turning Swiss automatic machine, boring, vertical boring, milling, hobbing, milling gears, drilling, sewing, broaching, grinding, shaping, planning, and gear shaping. Also presented in the table is the raw material form, the maximum and minimum size, typical production rate, material choice, typical tolerance, and typical surface roughness. Horsepower at the spindle of the machine is therefore given by the equation HP is equals to feed center times velocity over 333. HP is equals to feed center times velocity over 33,000. In metal cutting, a very useful parameter is called the unit or specific horsepower, which is defined as specific horsepower is equals to HP over MRR, given in the units HP per inches cube per minute. In turning, for example, where MRR is congruent to 12V feed rate times depth of the cut, then specific horsepower is equal to FC over 396,000 times feed rate times depth of the cut. Values for specific horsepower is also called unit power, and it's also given to the table. Here is the diagram of cutting speed and total forces generated by the speed. Specific horsepower values for the table are multiplied to approximate MMR for the process. The motor horsepower is then given to the equation HPM is equals to specific horsepower times MRR times CF over E, where E is the efficiency of the machine and E is the factor accounts for the power needed to overcome friction and inertia in the machine drive moving parts. Usually 80% is used. Usually the maximum MRR is used in the calculation. Here is a table of units for unit power and specific energy for cutting stiffness. Orthogonal machining, two forces. Orthogonal machining is carried out mostly in research laboratories in order to better understand this complex process. In OM, the tool geometry is simplified from the three-dimensional geometry to a two-force geometry. there are basic three orthogonal machining steps. One, orthogonal plate machining, or machining a plate in a milling machine, or low-speed cutting. Orthogonal tube turning, or end cutting a tube wall in a turning setup medium speed ranges. Orthogonal disc machining, or end cutting a plate tool feeding in a facing direction high-speed cutting. In oblique machining, as in shaping, drilling, and single point turning, the cutting edge of the cutting motion are not perpendicular to each other. In the orthogonal case, the cutting velocity vector and the cutting edge are perpendicular. The OPM, low speed plate machining, is using the modified horizontal milling machine where the table provides a cutting speed. OTT is done on solid cylinders that have bad groove machine and the end to form a tube wall, W, or a tubular workpiece can be used. The tubular workpieces can be mounted in a lathe and normal cutting speeds developed for the machining experiment. This setup has the advantage of being very easy to modify so that cutting temperature experiments can be performed. Using the tool chip/chip thermocouple method, the orthogonal cases is more easily modeled for temperature experiments. Here is the diagram for OPM, or the orthogonal plate machining, and OSD, front view of the OSD.
Continuation of Chapter 20, Fundamentals of Machining or Orthogonal Machining. So, what is chip formation? It is a part of the process of cutting materials by mechanical means using tools such as saws, lathes, and milling cutters. A chip is formed by a localized shear process that takes place over a very narrow zone. It is a high strain rate plastic deformation evolves out of a radial compression that travels ahead of the tool as it passes over the workpiece. Here you will see the picture of chip formation and its parts. Classification of chips. Currently, there are three types of chips, namely continuous chip, discontinuous chip, and continuous chip with built-up edge. Chip thickness ratio, or RC. It can be defined as the ratio of the uncut chip thickness T to the chip formed by the shear process TC. Its formula is RC is equal to T over TC, or AB sine omega all over AB cosine omega minus alpha. The workpiece passes the tool with velocity V and occurs at the onset of shear angle omega. The tool geometry is given by the back rake angle alpha and the clearance angle gamma. Here you will see the figure of the shear angle and its parts. Here you can also see the velocity triangle where V is equal to cutting speed, Vc is equal to chip velocity, and Vs is equal to the shear process velocity. Quick stop devices, or QSDs. The shear angle can be measured statically by instantaneously interrupting the cut through the use of quick stop devices, or QSDs, leaving the chip attached to the workpiece. Optical and scanning electron microscopy is then used to observe the direction of shear. Using sophisticated electronics and slow motion playback, this technique can be used to measure the shear velocity. Also, the vector sum of Vs and Vc equals V. These velocities are important in calculations associated with chattering. Here you will see the formula of consistency of volume, which is equal to Vc all over V. You can also see here the ratio of Vs to V. So Vs over V is equal to cosine alpha all over cosine omega minus alpha. Now we will talk about mechanics of machining in statics. The resultant R is composed of the friction force F and the normal force N acting on the tool chip interface contact area. The resultant force R prime is composed of a shear force Fs and normal force Fn acting on the shear plane area As. Using a dynamometer or a force transducer mounted either in the work holder or the tool holder, a third set of force is created in order to measure the two sets of forces. Circular force diagram is then developed in which all 6 forces are collected in the same force circle. Friction angle beta used to describe the friction coefficient M on the tool chip interface area, which is defined as F over N. Here you will see the formulas used in this topic. Now we will talk about polycrystalline metal. Its shear stress has been shown to non-sensitive to variations in cutting parameters, tool material, or the cutting environment. Its flow stress for a variety of metals plotted against hardness. Here you will see the figure. Now we will talk about shear strain and shear front angle. This figure is the Merchant's shear strain model, which is widely used in theoretical studies and industrial practice. It is also based on the stack of cards. Material shears on a single plane defined by omega in the direction of the shear plane. So the model combines psi and omega into omega, coupling them in any following analysis. So the Merchant's shear strain equation is cosine alpha all over sine omega cosine omega minus alpha. Here you will see the Black-Wang model. So the onset of shear begins at the lower boundary defined by omega with the material shearing in the direction of psi relative to this lower boundary. So another model is the Merchant's chip formation bubble model, where a new stack of cards model can be developed as shown in the figure. Equation of strain psi from the shear triangle is this. Other formulas used on this topic is specific shear energy, where US equals shear stress multiplied by shear strain. So there, and shear front angle, where psi is equal to 45 degrees minus omega plus alpha over 2. Now we will be talking about mechanics of machining in dynamics. So what is machining? Machining is a dynamic process of large strain and high strain rates. The process is intrinsically a closed-loop interactive process. From the top, inputs to the processes determine the chip load on the tool. The chip load determines the cutting forces which alters the chip load on the tool. The altered chip then produces new forces, then the cycle repeats, producing chatter and vibration. You will see on the figure on the right the whole process. So, chatter or vibration. This is the mechanism by which a process dissipates energy in elastic deflection. There are 3 types of vibration, namely free vibration, forced vibration, and self-excited vibration. You will see the 3 types of vibration on the figure on the right. So, what is free vibration? Free vibration is the response to any initial condition or sudden change. Amplitude of the vibration decreases with time and occurs at the natural frequency of the system. Next is forced vibration. This is a response to a periodic or repeating with time input. amplitude of the vibration remains constant for set input conditions and is linearly related to speed. Third is the self-excited vibration, where periodic response of the system to a constant input. The vibration may grow in amplitude and occurs near the natural frequency. Characteristics of chatter. There are 4 characteristics. First one is that there is a sudden onset of vibration, a screech or buzz or whine that rapidly increases in amplitude until a maximum threshold or saturation is reached. Second is that the frequency of chatter remains very close to a natural frequency, like a critical frequency of the machining system, and changes little with variation process parameters. The largest force displacement response occurs at resonance and therefore the greatest energy dissipation. Third is that the chatter often results in unacceptable surface finish exhibited by a helical or angular pattern, like it is pearled or fish-scaled, superimposed over normal feed marks. Fourth is that visible surface undulations are found in the feed direction and corresponding wavy or serrated chips with variable thickness. Next, we will be talking about important factors that influence chatter. So, first one is cutting stiffness, or KS. This material property related to shear flow stress, hardness, and work hardening. Next is speed. So, the rotational speed of the tool affects the phase shift between overlapping surfaces and the regeneration of vibration. Next is feed. This defines the average uncut chip thickness T and influences the magnitude of the cutting force. Fourth is the depth of cut, or DOC, which defines the chip width and acts as the feedback gain in the closed loop machining process. Next is the total width of chip, which is equal to the DOC times the number of cutting edge engaged in the cut. Next, we will be talking about cutting tool geometry. This influences the magnitude and direction of the cutting force, especially the amount of the force component in the modulation direction Y. As the back rake angle alpha increases or becomes more positive, the omega becomes larger, the length of the onset of shear plane decreases, which reduces the magnitude of the cutting force Fc. A reduced clearance angle gamma, which increases the frictional contact between the tool and workpiece, may produce process damping. Also, the size or nose radius, shape, or diamond, triangle, square, round, and lead angle of the insert all influence the chip area, shape, and the corresponding Y direction. Lastly, we will be talking about the stability lobe diagram. This is based on regenerative chatter theory that is an effective tool to predict and control chatter. Stability diagrams can be applied in machining processes to optimize the maximum depth of cut at the highest available spindle speed, thus improving the material removal rate and increasing productivity. A stability lobe diagram is formed by a series of intersected scallop-shaped borderlines of stability. Also, the intersections of the lobes denote the deepest stable cuts at various ranges of spindle speed. These optimum depths of cut have traditionally been found by graphical solution from the stability lobe diagram.